The actual amount of calculus in this next video is really very small. And in fact, if you remember from the first video in this section, you should be able to do it already. Now, most of this section is just remembering things about physics, okay? We're going to talk about Hooke's law and work a little bit, springs, stuff like that. But the actual calculus will be very short and it'll come up very quickly in this video. So let's imagine that this is me. That's a beard. That's an eye. Oh, it's a goatee, I guess. I don't know. Let's pretend this is me and I'm moving this object, which is has some mass. And I'm moving it some distance and I'm pushing on it with a force. Well, that we know from if we're going in a straight line, that the work done to move that mass from that distance in a line, that work is just going to be force times distance, otherwise known as WFD. Nobody ever says that, but there we go. Work is force times distance. I've coined it. You'll be hearing it everywhere in 10 years. Now, of course, this is only if there's a constant force. So what do you think is going to happen if the force depends on where we are? Do you think we might split it up into little pieces and add all those little pieces up together and get some sort of integral? Yeah, that's exactly what we're doing. I'm not even going to derive it all because it's just the same as the first video. The work is going to be the integral from one place to another place of that force function dx. Again, that's each little piece is the force on that piece times the length of that little tiny piece, and we add them all up together. That's what integration's all about. Okay? And that's all the calculus in this whole video. But there's probably some good information depending on how good you are with your physics. It's been a long time since I've done physics too. So hopefully it's smooth sailing. As a side note, some important things to note about work. The units for work are Newton meters. Whoa. Okay, it hasn't been so long since I've done physics that I don't know how to draw an M. Newton meters, which are the same as joules. And then if you really want to know what that is, I think it's kilogram meters squared per second squared. That's what I've written down in my notes. Again, all three of these things are the same. I don't think we're doing any imperial units for work. Okay. These are the units of work that we're going to be using, and they all mean the same thing. Okay. So anyway, let's get into some. This is only in a straight line, by the way. This is work along a straight line. Totally fits. Let's remember some things about springs. Okay. Let's say I've got, nice coily spring, and there's some object right here. That is going to be a spring at equilibrium. Wherever the resting point is. If you just attach it and let the spring chill, that's equilibrium. Okay, wherever it can chill. That's the very precise definition. Sometimes, of course, you can compress the spring. That's going to be negative x. It requires a force to stay compressed. Ooh, force. He said the F. Force, okay? And then, of course, you can do the exact same thing. Sometimes you can really stretch out that spring. That's going to be positive x. And that will be stretched. The book also wants me to tell you that the word here is elongated. I'm not going to write down the word elongated. Come on. It's stretched. Okay, but it's fine. If you want to be technical, elongated I think is a word that's used often, but I'm not going to be using that word, so I'm not writing it down. All right, so remember, positives, negatives, all that stuff does matter because the zero, that's the important thing here for these springs, x equals 0 is where the spring is at rest. That's going to be very important. Okay, and then we also have Hooke's law, which says that the force required at any x, again, x equaling 0, is going to be that at rest point. So the force required to keep something at any position for a spring is just k times x. And k is just some spring constant. It depends on the spring, depends on the mass. Wait, does it depend on the mass? Yeah, it's got to depend on the mass. It depends on the situation, basically. Okay, and we're assuming all of this has no friction. It's very slidey, okay? If friction's a thing, it's a little different. Okay, so that is also going to be an important thing that we're going to be using in this section. So let's use it. Example 3. Let's put it all together. Suppose it takes a force of 10 newtons in the negative direction to keep a spring compressed 0.2 meters from equilibrium. How much work is done to stretch it to 0.5 meters from equilibrium? And again, that's going to be from rest. So we're not actually moving it from the 0.2 compressed to the 0.5 stretched. It's just from rest to 0.5 stretched. This piece of information is just giving you information that we can use later, but it's not actually part of this physical situation. Okay. And then follow-up question is this same work as compressing 2.5 meters from equilibrium? So there's two questions here, and I want you to think about the second question first. Just what you know about the real world as opposed to the fake mathematical world. What do you know about the real world? If you stretch a spring an amount, is that the same work required as compressing the spring from that amount? Is it the same work being done? Think about it. Come up with a guess. And we're going to use some calculus to see if it's true in this simplified, frictionless world. Oh man, I had such a good terrible line prepared. It's going to be like, all right, now we talked about, the work and force equation. Now we talked about the work and force equation. Who's ready for spring break? I know I'm looking forward to spring. All right, never mind. Okay. The ship has sailed, but we jumped in the water anyway. Okay, let's do the problem. So we're asked how much work is done. Well, that's easy. Work is just force times distance. Oh, but the force depends on where the mass is, where the spring is. So it's not constant. The work is now going to be the integral of force using that formula. Oh yeah, and then we can edit this a little bit. We know what A and B are. It's going from equilibrium up to 0.5 meters. And then we just replace this with the force equation, and I don't see a force equation. We're going to need one. Oh man. If only there was someone to save us. Hook is saving the day. Don't believe the lies of Peter Pan. The force is just K times X. Oh, that's great. That's great. Whoo. Force is Kx. So we can just integrate that. But what's K? We're iteratively getting more and more information, but we're still missing K. K is a spring constant for our specific situation. And that's where this comes into play. It takes a force of 10 newtons to have a spring compressed at point 2. Let's translate this. When x is negative 0.2, right? Because it's compressed. Compressed is negative x. If x is negative 0.2, what is the force? The force required is going to be negative 10 newtons. Again, force is a direction-full quantity. It's not a scalar quantity. It's a vector quantity. The direction matters for force. Positive means one way, negative means the other. And for springs, we just said positive means stretching or elongating. Okay, so that tells us information. We use that information to solve for K. So the force is negative 10, and that's K times X, which is negative 0.2. Oh, so K is just negative 10 divided by negative 0.2. The negatives cancel. That's dividing by a fifth, multiplying by 5. The force is 50. Sorry, the K is 50. And right there. Okay, well that we can use that. So f of x is 50x. Oh, so now we can use that to go over here to the white part and get that the work is 0 to 0.5 of the force, which is 50x dx. Great. That's an easy integral. The phrase, you snooze, you lose, doesn't apply here because this integral is so easy you can snooze and win. I'm on fire today. So the antiderivative is going to be x squared over 2. 50 divided by 2 is 25. That's our antiderivative here. Evaluated from 0 to 0.5. And again, we can always check our antiderivative. If we take the derivative of this antiderivative, do we get the integrand? Yes, we do. Great. So plug in 1/2. 1/2 squared is a quarter. 0 squared is 0. Quarter of 25 is 6.25 joules. Because everything is in the right units for us to use joules, right? Yep, we don't know the mass, but it doesn't matter. We know the spring constant. Spring constant. Great. And then this is in meters, so we are good to go. So that is our answer for the first part. Now, is this force the same as compressing it to 0.5? Well, if we compress it, it's going to be the same force function, same integrand. But now we're going in the negative direction. Well, this is an odd function. An odd function, it's a line. Going in the positive direction, going in the negative direction are going to have the same area. Yeah, force or the work should be the same. Okay. That's this video. That's the work in a line. Work with linear force. And in the next two videos, are where things get a little bit less straightforward, a little bit more fun, okay? So these videos, we have nice formulas. I'll talk about it in the next video. Just do the work. Just have a good time. Enjoy your innocence while it lasts. Bye-bye.